workshop. And our next speaker is Aida. It seems to me that almost every time you are the speaker of the first day of our workshop. Is this true?
I think so. Maybe only one time was not the case.
Just right now. Yeah, I understood that every time you are one of the first speakers of our workshop. And I'm really happy that again, you are one of the first. So the floor is yours.
Thank you, Elena. Thanks for the nice introduction. And also thank you, of course, for inviting me here once more. I'm very happy to be in Russia. Hope one day we can meet in person, all of us. So my talk is going to be about weight-equitable partitions of graphs. And this is work I started doing 2 years ago, well, 3 years ago, maybe. And it's based on 2 papers. One already appears in a journal. The other one has been recently submitted with my PhD student and a colleague from Eindhoven University. So actually, if you never heard what a weight-equitable partition is, that's the same as a weight-regular partition. I'm not sure that says anything else to you, but just to make sure that we don't get confused, maybe sometimes I'm going to be speaking about equitable or regular. They are the same thing. They are the same type of partitions. So this is the outline of my talk. I will start trying to give you a bit of a background to the topic and also a bit of motivation, because you might not have heard of these weight partitions. So I hope to convince you that they are useful with this part. In the second briefly part, we will just see some expected spectral properties of such partitions. And then we will focus on algebraic characterizations, in particular 3 types of algebraic characterizations. We found some more, but I want to highlight the ones I think they're the most maybe useful or relevant. Next, we will go see an application of these new partitions to graph theory. And in the last part of my talk, I will focus on some recent results which are regarding how to compute such weight-equitable partitions. We will see that it's a very hard problem, but maybe in some cases we can do something. And I will finish with some closing remarks that mostly include open problems. Okay, so let's get started. I always like to start with this graph. Mainly, well, I have been living in the Netherlands for 10 years, so this is maybe about time to show it that I'm not only from Barcelona, but I also I'm very happy living in the Netherlands. And this is actually called the Dutch windmill graph or the friendship graph. So it's always nice to be here with friends. And well, I put this graph for several reasons, but first let me fix the notation. And I'm going to be talking about eigenvalues of the adjacency matrix of a graph. I will denote them as lambdas whenever I consider them repeated, and as thetas whenever I consider them distinct. So it depends on the proof or the result. You need to consider only the distinct eigenvalues, the d+1 distinct eigenvalues, or all of them with multiplicity. And the reason I also picked this graph to start is because it has a nice partition. And maybe you heard before about equitable partitions, but if not, you can see that if you pick in one vertex cell, if you partition the vertex set such that you put the middle vertex alone and the rest together, that partition has a lot of regularity, a lot of symmetries. So we want to study that phenomenon and extension of this phenomenon. So basically, equitable partitions are partitions of the vertex set, as I just highlight. For example, in this case, I have this vertex, this graph. I partition the vertex set into 2 sets, V1 and V2. And equitable partitions are those such that whenever you look at the neighborhood of vertices in the same vertex set, in the same cell, they have the same number of neighbors in each other cell of the partition. So if, for example, you look here at this graph V, V could be any orange graph in this graph, because they all belong to V1. V has exactly 2 neighbors inside V1, inside the orange partition, and exactly 1 neighbor in the V2, in the other cell. And this is a bit related to the quotient graphs that we just saw in the previous talk. So actually, given a partition, not necessarily equitable, you can always calculate what is called a quotient matrix. And by definition, it contains the average row sum of the blocks into which you partition your adjacency matrix, or the number of edges, the average number of edges that are between 2 vertex sets in your partition, roughly speaking. So it's important to realize that partition equitable means that these numbers, these entries of this quotient matrix, which summarize the partition, they only depend on I and J. So they don't depend on which vertex are you picking. So whatever orange vertex I pick, they will always have these two here and this one here, etc., etc. So these numbers, which are the entries of the quotient matrix, we call them intersection numbers or entries of the quotient matrix. And they are constant for whatever vertex you pick in the same cell. That's an important thing to remember here. So equitable means that these entries, this number of edges, are the same for whatever vertex you pick inside the same cell. You've probably seen this before. Just a quick recap. Representing partition is usually done using something called a characteristic matrix, which just contains the characteristic canonical vectors, telling you it's a 0, 1 vector, telling you wherever your vertex is in V1 or in V2 or in Vm. So in general, I'm going to be partitioning into M sets, and M is strictly smaller than N usually, otherwise it's trivial. So why are we interested in partitioning graphs? Well, roughly speaking, is ranking graphs. It's interesting because from the algebraic point of view, you still preserve part of the spectrum. So here I put you the example of the Petersen graph, which has a nice distance partition, as you might know. And this is the corresponding quotient matrix of the Petersen graph. And here in this case, we recover all the spectrum. We don't recover all the multiplicities, obviously, but we recover at least these 3 distinct eigenvalues. This is not always the case, but in general, this is a folklore theorem. So we just put here the book reference, but I don't know exactly who proved it first. It's known that every eigenvalue of this quotient matrix is also an eigenvalue of the original matrix, of the adjacency matrix of the original graph. Okay. Okay, and why are these partitions, equitable partitions, interesting in algebraic combinatorics? You might know that they occur naturally in all these graphs we study in algebraic combinatorics, distance regular, but many others. And not only that, but these equitable partitions have only been very useful to prove graph bounds for NP-hard parameters to compute, for example, the independence number of a graph, the alpha. Basically by using interlacing. So, okay, the question is like, can we extend equitable partitions? How can we do that? So one way you could think is like, okay, why don't we just assign weights for the vertices of the graph? That could be an option, but which weights do we pick for that? We should pick some weights that somehow regularize the graph. Maybe later you understand why this is an important property. So how has been done in the literature, how was done before, it was using the Perron eigenvector. Because it has many nice properties. So given a connected graph with a certain spectrum, we know by the Perron-Frobenius theorem that the eigenvector corresponding to the largest eigenvalue, lambda1, has positive entries. That's a very important property for what we want. And then all other eigenvectors have negative entries. So for example, if you pick a regular graph, you know that the Perron eigenvector has all 1 entries. So you can already see that for regular graphs, these weights are not interesting, but we want to extend things to non-regular graphs, and therefore the entries will be non-trivial here. So this new is going to be called the Perron eigenvector in this talk. So if now we want to extend the theory for equitable partitions to weight equitable partitions, what we do is we need to define the weight quotient matrix. That was first defined by Fiol, I believe, in 1999, with entries called the weight intersection numbers. And this is nothing else that instead of summing over all the number of neighbors you have in the other cell that are adjacent to you, now you compute the sum of the weights of all the vertices which are adjacent to the vertex you're looking at. So you fix a cell, you fix a vertex in a cell U, and then you look at all the vertices which are in the neighborhood of U, which are in another cell. And then you add all those weights, the corresponding entries of the Perron eigenvector. And then you normalize by the Perron entry corresponding to the vertex you are analyzing. Okay, and then maybe one important remark here, and this is why we said you cannot pick any random weight, but you want to pick the weights using the Perron eigenvector, is that if you add up all these weight intersection numbers, so this sum here, up to M, that gives you actually a type of average degree of that vertex, a weighted average degree of that vertex in particular. And that sum corresponds to the largest eigenvalue. Okay. So basically weight equitable, what we need to remember is like, it's the same concept as for equitable, but now indeed, it doesn't matter which vertex you're looking at in the cell, because all the vertices in the same cell will have the same VIJs weighted in this case. So whenever I'm talking about results about the weighted case, you have an asterisk on top. And here is the same example as before, but now using the weights. So now you calculate the Perron eigenvector. I give you here the weights per vertex. And then you can calculate the weight intersection numbers. And then you can notice, I mean, this is an exercise for the reader, but whatever V you take, V could be any orange vertex, you get the same number here. And the same happens for the black vertices. They always have the same intersection numbers. So this is the equation matrix corresponding to this weight equitable partition. And then here we can indeed see that the sum gives you the largest eigenvalue of this graph. And maybe a less trivial case, because here we are just doing with 2 partitions. You could also have 3 partitions. Imagine this in particular is also regular, but weight regular as well, weight equitable. So this is the Perron eigenvector, and then you can easily calculate the intersection, the weight intersection numbers, and convince yourself that they are constant for every vertex which is in the same set. So all of these guys have the same weighted intersection numbers. So in general, weight equitable partitions don't need to be equitable, and this is one of the smallest examples one can find. Well, maybe not the smallest, but one example one can find. So this is clearly not a equitable partition, but you can check the definition that we just saw. You can convince yourself this is actually weight equitable, and it's actually a bipartite graph, which is always weight equitable. Okay, let me now mention a little bit about the origin of these weight equitable partitions, because this is not something we invented. The origin, I would say, goes back to Hoffman bound. The reason why they were introduced goes back to Hoffman bound in the 70s. And it's a very famous bound because it's very simple. It gives you it gives you a lower bound, which is easy to compute in polynomial time because the eigenvalues are easy to compute for an MPH parameter. And then it tells you the ratio of these largest and smallest eigenvalue lower bounds the chromatic number. And the first result the first time that this result by Hoffman was extended to non-regular graphs, to general graphs, was done by Hammers in 79. I believe it was in his thesis first, or maybe a bit earlier than this. And it was in this paper, the famous interlacing paper. So if you search for interlacing eigenvalues, this is probably the first paper you find. And in the proof of this extension of the Hoffman bound, this first statement here, he used weights for the characteristic metrics. So we saw that usually you represent partitions using a characteristic matrix that we call S. Normally has ones or zeros. So here, Wieland, what he did is like he used the corresponding entry on the Perron eigenvector. And that allowed him to actually using arguments by interlacing to extend Hoffman's proof to general graphs. So I would say this was the origin of weight partitions, not necessarily equitable here, but weight partitions. But they were later on, quite some time later in the 99s, they were formally defined and used by Garriga and Fiol. So if you want to see all the setup of notation, this is the paper to check. And then actually what happened later on the same year, actually, Fiol extended all the theory that was known for eigenvalue interlacing to weight. It was known for equitable partitions, so he extended it to weight equitable partitions. So maybe just a quick recap. Eigenvalue interlacing has different types. There is the Cauchy interlacing, which is maybe the most famous that you might have heard, where you consider the principal symmetrics. But there is also another type of interlacing that was introduced by Hammers in his thesis that is called well, I don't know, Hammers interlacing, where he uses equitable partitions of a graph, basically. And that's what Fiol extended in this paper. So why is one using equitable partitions? We already saw one result, that a powerful result that was extending Hoffman's bound for general graphs, but is there something else one can do with equitable partitions? The answer is yes, because I have already mentioned it's a powerful tool to extend results that are known for regular graphs to non-regular graphs. But let me give you here some examples. So Fiol, Garriga, and Yebre in 96, they actually already gave weights. They didn't call it weight distance regular, but they already used the same weights, the Perron eigenvector entries weights, to introduce what they call locally pseudo-distance regular graphs. So here, instead of having a distance regular graph, you have a weighted intersectional array where you're not counting again number of neighbors, but you're counting the average of the Perron entries. Sorry. And in the 99 paper, actually, Fiol and Garriga also provide new spectral characterizations of distant regular graphs around a set of vertices and completely regular codes by using these pseudo distant regular graphs or weight distant regular graphs. And also an important result is that the famous spectral excess theorem to characterize when a graph is distant regular was also extended to irregular graphs by Li and Wang using the same weight partitions that we just introduced. Well, this is the result I just started with, the extension of Hoffman's bound for. So these are bound type of results. So not only for characterizations, but people have been also using these weight partitions for extending bounds, type bounds. So this was done for the Hoffman bound. It has also been done for the Lovász-Shepherd bound for the Shannon capacity of a graph by Thiol. And we recently also use it to push some bounds for the more general independence number, the K-independence number, the extension of it. So again, keep in mind that equitable and so not all weight equitable partitions are equitable. So this is another example here. You can easily see that, for example, the orange vertices don't form an equitable partition because they have different number of neighbors. So in general, this is indeed the case. The converse is not true, but there are some relationships, trivial relationships that are known. For example, they are summarized in this table, depending on the number of cells. So if you take the extreme cases into which you partition your graph, so imagine you partition your graph into single vertices, or you partition your graph into two sets, or you partition your graph into, all together, or two sets, or one by one, vertex by vertex. So in that case, you can easily extrapolate what happens for equitable, when is that equitable and when is that weight equitable. But what is a bit intriguing here in this theory is like there is not much known in between. So say we partition your graph into three vertex set, into three cells. Can we say something about when that, can we find sufficient or necessary conditions when that thing is weight equitable? That is really wide an open question. A very trivial observation or remark is that if we have a weight equitable partition and the Perron eigenvector has constant entries over the cells of the partition, that gives you a condition if and only if that happens, if and only if the partition that you started with is equitable. So here is a very tiny example of a weight equitable partition, which is equitable because indeed it's constant. The Perron entries, which are indicated here as the weights in the vertices, are constant over the cells of the partition. So let me give you some spectral properties of these graphs, of these partitions. I mentioned that normally you use a characteristic matrix to indicate as an indication of how you are partitioning your graph. Here we use a weighted normalized characteristic matrix. It doesn't really matter now, it's just a technical detail, but it's just you put some weights, you calculate it like this, you put the weight of the vertex that you're looking at in the row contains the vertices, the columns contains V1 and V2, the number of vertex sets. So instead of 1 and 0, you put this weight entry here in the matrix representing the partition. And then similarly, you can also calculate the entries of the weighted normalized quotient matrix. Okay, so don't bother too much about this. It's just technical, but one can do the same exercise as we did before for non-weighted case, but now with the entries of the Perron eigenvector. Okay. Okay. So the important result here is that the same properties we had for the equitable case and for the for the partition case, the classical case without weights, still hold for the weighted case. So you can prove that the weighted normalized equitable quotient matrix V has still the same large eigenvalue, which is a very important property, as the original adjacency matrix of the graph. And you can also easily show that all the eigenvalues of this quotient matrix are also eigenvalues of the original adjacency matrix of the original graph. Okay. And then again, the same properties that hold for the characteristic matrices, which were orthonormal in the non-weighted case, still is maintained here by the definition of this matrix. And you can also easily calculate, so that's why I say don't bother about using the definition of weight quotient matrix, because you can easily calculate the weighted quotient matrix by just using the right weighted characteristic matrix, adjacency matrix, and then the matrix transpose. So now I'm gonna give a bit of motivation. Well, not yet, but I'm gonna highlight a bit of motivation of why one wants to know when these partitions exist, these weight equitable partitions. So in the next session, we will see that sometimes it's useful to understand when the graph admits a weight equitable partition. I'm not saying yes, why, but this is sometimes the case. It's something that has not been too much studied yet, but seems the case. So if that's the case, if we assume this is the case, we're interested to find characterizations and conditions to know when some partition is actually weight equitable. And the first characterization I managed to prove involves what I call generalized double stochastic matrices. So I will describe it in a second what it is. And then basically using certain stochastic matrices, we just can prove a characterization. So the only characterization I could find in the literature was by Fiol in the 1999 paper, where he proved that if this relationship between the weighted characteristic matrix, adjacency matrix, and the quotient matrix holds, that gives you if and only if condition for the partition to be weight equitable. And this actually happens equally for equitable partitions, so it's not too surprising. We know what a double stochastic matrix is. Probably is a non-negative, is a matrix with non-negative entries, such that the rows and columns adds up to 1. So, for instance, permutation matrices is the easiest example. I'm going to be denoting the set of double stochastic matrices by this omega. And then maybe it's important to notice here that this omega is actually a convex polytope, since it contains just linear relationships between the adjacency matrix and this matrix X. So it forms a convex polytope. It's not too relevant for now, but this is something maybe to think about in the future. And Gottschild in a 97 paper, he managed to prove a characterization of equitable partitions using double stochastic matrices. So basically, he say if we have an equitable partition, then the adjacency matrix and this characteristic matrix product needs to commute. Remember that S transpose S is the identity, but this is not necessarily the case. And the other way around. If these two matrices commute, then the partition needs to be equitable. So the main question that pops up here is like, can one extend his result to weight equitable partitions? The answer is yes, but you need a slightly different concept. You cannot just work with double stochastic matrices. You need something a bit more relaxed definition. I call it generalized double stochastic matrices. I'm not sure if they exist, so please correct me if that's the case. I asked Rualdi at some point, that do these things have a name? He said, I never heard of it, but could be. So the main difference is like you don't request to have row sum and column sum equal to 1, but you need to have constant row sum and constant column sum. So let's call it for now generalized double stochastic matrices because they almost hold the same properties as before, just dropping the condition of equal to 1. And they also, of course, there is still a convex polytope. They still form a convex polytope. And then one can extend with a bit of technical work, but one can extend Gottschild's result for weight equitable partitions. So it's the same thing, but then instead of using the characteristic matrix of a partition, use the weighted characteristic matrix. Okay. And then, well, as a corollary, you know that if a partition is weight equitable, if and only if this product of weighted characteristic matrices belongs to the polytope of the generalized double stochastic matrix. Okay, another characterization that we managed to show is using fractional automorphism. So let me first refresh the memory of what is that. We all know what a graph automorphism is. It's just an isomorphism from the graph to itself. So there should exist the permutation matrices such that the adjacency matrix permutes with P. But then fractional automorphism, it's a bit of, again, more relaxed definition because it assumes you need a double stochastic matrix. So it's not necessarily a 0-1 matrix, but it can be, for example, this matrix here. And then we have a fractional automorphism if we have this relationship between the double stochastic matrix and the adjacency matrix. So before I continue, there was a result. I don't remember now if it was in Gottschild's paper or in another paper that uses linear programming symmetries and also quotient matrices to prove a similar type of characterization, where they prove a characterization of equitable partitions using this fractional automorphism or fractional isomorphism, because we actually are just using X here. But unfortunately, this is not so trivial to extend for weight equitable partitions, because of course you have many more things there that you need to control. It's not just counting neighbors. So we had to massage a bit the result, like we don't get if and only if. So basically we had to define, well, given a double stochastic matrix X as before, we define a directed graph G of A, which has adjacency matrix 1 whenever the entry of the double stochastic matrix is non-zero and 0 otherwise. So this 1 is actually a directed edge because we're talking about a directed graph here. And then let Px denote the partition of the n vertices into the strongly connected components of this directed graph GA. So then we could show that if this double stochastic matrix commutes with the adjacency matrix, then this partition should be weight equitable. And then to go the other way around, we had to do another trick here because it does not extend right away for any double stochastic matrix. That was the main issue we encountered. So we defined a matrix which does not have to be double stochastic. It's a bit of more general matrix with these entries where we are using the Perron weights again whenever these two vertices are in, whenever the two vertices you are looking at are in the same partition, in the same cell of the partition, sorry, or 0 otherwise. And then we could show that if the partition is weight equitable, then it needs to hold that there is this commutativity property between this matrix, not necessarily double stochastic, and the adjacency matrix. So this is, for example, an example, tiny example of matrix, which is clearly not double stochastic, but that holds this property that lets you say, okay, if you give me a weight equitable partition, then this needs to hold. Okay. And finally, maybe a different flavor, I would say, characterization of weight equitable partitions was done using Hoffman type polynomial. So maybe, I don't know if you remember what the Hoffman polynomial is, but it's just x minus the product of the distinct eigenvalues, except the trivial one, the k, the degree. So Hoffman in 63 gave a very important result, actually, characterization of regular graphs in terms of the Hoffman polynomial. In terms of a polynomial, he didn't call it Hoffman, but in terms of a polynomial. But then at the end, people have been using it in the literature as Hoffman polynomial. So this result was extended much later by Li and Wang again to non-regular graphs. Actually using, again, it's the same paper, the weight partitions. And then we also managed to prove an analogous result for biregular graphs in 2013 with Viola and Dalton. So this is a bit how the result for two sets looks like. So I just want you to see like a little bit the story, because this is how what we are going to extend next. So the main question I had is like, can we find Hoffman-like polynomial to characterize weight regularity? And the answer is yes, and this is this theorem. So basically, the Hoffman-like polynomial to characterize weight equitable partitions looks like this. So it has a lot of structure, as you can imagine, and it contains the weighted intersection numbers. So these are the entries of the quotient matrix of the weight partition. So I want to give a sketch of the proof because it's just quite intuitive, I think, but yeah, also to have a proof. So first, let's go from weight equitable to there is such a polynomial, like we can find such a polynomial, Hoffman type polynomial. Main tool that we always use is spectral decomposition theorem. So we can decompose the adjacency matrix using the idempotems corresponding to each distinct eigenvalue. So careful here, we are using distinct eigenvalues. Then we also know that the Hoffman polynomial, forget about the weight for now, the Hoffman polynomial can be computed as this product using the distinct eigenvalues here. And then using the fact that any polynomial, so any power, any linear combination of the adjacency matrix also holds the decomposition theorem, the spectral decomposition theorem. We can actually just apply the Hoffman polynomial using this property of the spectral decomposition theorem, and then we get, if we use the right H here, we get that only the eigenspace corresponding to the largest eigenvalue, to the zero, theta zero, remains. And then it just, the rest of the proof is just like calculating such a idempotent. And then the other direction, it follows quick because we are assuming, and this was a bit of an issue in the proof, like you cannot have if and only if without the assumption that you have constant entries in the Perron eigenvector per cell. So that was a bit of the only drawback of this result. So the other direction almost follows right away by this observation that the Hoffman polynomial on the adjacency matrix can be computed using the Perron eigenvector like this. And because we are assuming that the entries are constant over each cell of the partition, then it follows almost quite quick that needs to be weight equitable. Okay, so maybe just one more remark regarding why polynomials are related to weight regularity, to weight equitable partitions. Weight equitable partitions, we saw, or we have been maybe smelling it, that they maintain the structure of the Perron eigenvector corresponding to the larger eigenvalue. So if you have a weight equitable partition, you guarantee you have constant entries on the corresponding entries of the Perron eigenvector for vertices in the same cell. As a consequence of that, we know that for a regular graph, we know the Perron eigenvector is constant, is the O1 vector. Then we would obtain the theorem by Hoffman. So G is regular and connected if and only if the Hoffman polynomial or a certain polynomial which he proved is unique, evaluated in the adjacency matrix, gives the O1 matrix. So J is denoting the O1 matrix. Okay, so I think this was all from the polynomial point of view. And this was also all from the point of view of characterizations, of algebraic characterizations. Now I would like to give you an application of weight equitable partitions. And it's an application to graph theory. So again, we go back, we are really talking a lot about Hoffman today. We go back to the famous Hoffman bound for the chromatic number of a graph. This is Hoffman. And some authors define a Hoffman coloring so a graph has a Hoffman coloring whenever the graph holds Hoffman bound with equality. And maybe something I like to mention here is like Hoffman bound, this bound in particular, not the previous result, but this bound is always a bit tricky because nobody really knows which paper to cite. It's an unpublished result by Hoffman, although it's a very popular result. So recently, Willem Hamers decided to write a review paper trying to explain a little bit of the history and the main highlights, or main results related to Hoffman bound. So if you're interested, it has been recently published in linear algebra and applications. So let's go back to Hoffman bound with equality. We know that all bipartite graphs have a Hoffman coloring, obviously, because the spectrum is symmetric. And therefore, we also know that such bipartition, I mean, we know that any bipartition is always weight equitable. However, there are not many infinite families of graphs which meet the Hoffman bound for the chromatic number, or we don't know them at least. I mean, there are probably, but we don't know them. We don't know how to find them. And related results in this direction, so this is what I just mentioned. For the bipartite case, it's easy because it's trivially holding. The Hoffman bound is trivially holding with equality. But for larger than 2, for chromatic number larger than 2, no match is known. So I would just like to point out two results in particular that are known. This paper by Blockhuis, Brouwer, and Hamers provides some necessary conditions for a graph to be 3 chromatic in terms of the spectrum. And then also this other result that provides by Cullen and Kiao that provides a complete classification of 3 chromatic different regular graphs. So it's a follow-up of the previous paper. But besides this, not much more is there in the literature. So what I managed to prove in that paper in 2 years ago was that if a graph has chromatic number chi and a Hoffman coloring, means that the graph is holding Hoffman bound with equality. So 1 minus lambda 1 divided lambda n equals chi. Then the partition defined by the color classes needs to be weight equitable. Okay. So this is giving kind of a condition, because what we can rephrase now as a corollary is like if the graph has at least one edge, because otherwise the Hoffman bound does not apply, and the vertex partition defined by the color classes is not weight equitable, you can improve Hoffman bound by 1, so you can go 1 up. So of course, this is a bit of a chicken egg problem because, yeah, you need to know the chromatic number, and then is kind of a bound that is a bit implicit somehow, but this is giving you a condition under which you can improve Hoffman bound by 1. Okay. And this is all using weight equitable partitions, as you can see. And the proof is basically by interlacing the proof of this result, this theorem. So here I like to give an example of this case. So this, I think I put this graph before as an example of weight equitable partition, which is not equitable. And this is a graph, you can calculate the spectrum and you can convince yourself that it holds this case, the Hoffman bound holds with equality here. And yeah, well, the weight color class, the color class partition is actually a weight equitable partition. So this would be an example of graph which hold this bound. So basically, if a graph does not have a weight regular partition, it cannot have a Hoffman coloring. That's a bit the takeaway of the previous result. So it cannot hold Hoffman bound with equality. So this previous corollary, this previous result I proved, it could be useful for finding new families of graphs, of non-regular graphs, for which the Hoffman bound holds with equality or can be improved, because maybe there is some extra condition under which you can even improve the bound. Okay, so this is all about the algebraic part. So now I would like to mention some results about calculations or computing with equitable partitions, because we realized nothing was done regarding this. So basically, there is no results yet in the literature trying to approach with equitable partitions from the computational point of view. There is not even much done for equitable partitions because it's a really hard problem. I mean, we really don't have many results there. Otherwise, also that would help to prove the isomorphism problem, which is also not known to be solvable. So let me start a little bit this approach, this different view on weight equitable partitions. So basically, there are two ways you can partition a graph. You can partition your vertices into many cells. Then you have a very, very refined partition. We call it the finest partition, is just vertex by vertex, but that's a trivial one. Or you can have something with the smallest amount of vertex sets. So say 2, because 1 is just trivial. So what we're gonna think is like, are people in the literature in the algebraic community more interested in finding fine weight equitable partitions or coarse weight equitable partitions? And actually we realized, looking at the previous papers, that depending on the application, different levels of coarseness were required. So let me give you 2 examples. The bounds, for example, by Svetkovic, the inertia bound that was proved by interlacing and was extended using weight partitions for by Fiol, that only requires 2 cells, because you just partition your graph into 2 sets, the independent set and the remaining vertices apart. But for example, all the results where spectral characterizations of pseudo-distant regular graphs were done, those results by Garriga, Fiol, they basically need as many cells, as is a bit of expected, as many cells as the diameter plus 1. So it's a distant regular graph, and therefore the type of partition you want really depends on the diameter. So as you can see, there is no one best option here. Like it seems like the authors, I mean, both of them could be beneficial to know how to compute. That's a bit the takeaway. But in general, it's important to keep in mind that the coarser it is a partition, the more shrink it is. So the more condensated it is, the less information you need about the original graph. Okay? So this is the slide I mentioned before, because indeed this is a nice partition because you recover the whole spectrum, but this is not always the case. So the focus of this computational part is about calculating coarse weight equitable partitions, coarsest, not the trivial one. And yeah, basically we will see what has been done for equitable partitions to calculate the coarse weight equitable partition first. That's what I'm going to explain. And then we will see what we can do for the weighted case, if we can do something. And then we are also going to focus on the other extreme, which is one of the most classical fine weight equitable partitions or equitable partitions, which is considering cells 2 by 2. So you put vertices in pairs in your partition. We're going to call that key homogeneous. So key in this case is 2 because we put them in pairs, but key can be a constant number. So you put constant number of vertices in each vertex set. So just one thing we realized is like finding general complexity results is hard. So there is no hope at the moment to prove the complexity of the calculating weight equitable partitions, because it's not even known for equitable case. So it's much harder for the weight case, because then you get the algebraic properties of the Perron eigenvector, which are also not well understood. So we will start with some regular cases and these 2 homogeneous cases, 2 homogeneous partitions. We will focus on that. But before I go to that, let me mention that for equitable partitions, we know how to calculate the coarsest one, and it can actually be found in polynomial time. This was done by Bastard in the 99. Sorry. And it's based on a color splitting argument. So he starts with all the vertices in black. So here you already paint them. And then he starts coloring the vertices based on the degree first, in the first iteration. So basically using some color splitting arguments, he keeps refining his partition a bit more and more. But this argument of color splitting was not created by Bastard, apparently. It was already known in some other contexts, like, for example, algorithms for minimizing finite automata by Hoffman in the 70s. So this has been a kind of argument around in the algorithmic community. But you might wonder, like, this is the first thing we thought, can we extend this to weight-equitable partitions? And it looks like the argument works, because actually the only thing you do is, like, instead of looking at number of neighbors, so what you do is, like, you first start with the degree, and then you look at number of neighbors that has a certain color and try to keep that constant for vertices in the same vertex set. But you would think, like, okay, adding weights is the same criteria, but then you look at the average, the sum of the average of the weights of the neighbors of that vertex and try to make that as constant as possible. So the argument seems to work. However, the problem fails, or the extension fails, because the starting partition that Bastard consider is just weight equitable. It's just everything in one, so it's already weight equitable. So there is no hope, because whatever you do, you will already be picking a certain partition to start. So the argument was not extendable right away. So this is the case, actually. He starts with all the cells in one, and then he starts coloring using the degree and using the number of neighbors of each color. So we're here. So what we thought is, like, okay, it seems hopeless, at least for the coarse weight equitable carries, to extend that, but maybe we can say something.
Aida, I cannot hear you. Is everything fine with connection?
She's coming back. Her Wi-Fi failed for a minute.
Yeah, it seems so. Yeah, thank you, Martin. Thank you very much. Yeah, yeah. We are looking forward for the connection. Yeah.
Apparently, you will have to let her in again.
Oh, excuse me?
You need to allow her to enter once more.
Well, for Aida.
Yes.
Sorry, Elena, I had an issue.
Oh,
with
yeah,
my
it's
Wi-Fi.
fine. Okay, good. Yeah.
I don't know
Everything
where did you lose me? Let me go back.
Yeah, right here. Yeah.
Ah, perfect. Sorry about
Well,
that.
actually, we didn't lost you. Yeah. Okay.
Okay, let me then continue 1 second. Sorry about that. So, okay, I was mentioning that we focus on the two homogeneous equitable case because it was one of the classical fine cases. So it's a fine partition. You just have cells of size 2. And then we realized, okay, well, let me see 1 second. I was here, yeah. Okay, so we could prove that a two homogeneous equitable partition, so one like in this example, happens even only if the graph has an automorphism, which is an involution without fixed points. So, for example, this is the case. So this is a necessary sufficient condition we found. However, the bad news is like there is this Lubick result in the 81 that proves that deciding whether a graph has a fixed point-free automorphism for the two, so exactly what we wanted, is NP-complete. So that already makes you a bit hopeless, which means, I mean, this implies that finding equitable two homogeneous partitions in general is NP-complete. So there is not hope to solve it in general for general graphs. However, maybe we can explore the structure of some graph class in order to find some algorithm. And this is what we did. So we start looking at, we start brainstorming, okay, which graphs could be good candidates to find an algorithm and find this equitable type of partitions. And also, before I mention how we did it, it's also important to realize that the argument is not, obviously, it is not possible for equitable. It's not possible for weight equitable. So we cannot extend the argument, the proof argument, unless the partition is also equitable. But when does it happen? So we saw that in general, we cannot decide whether a graph admits an equitable partition into cells of size 2, the homogeneous, two homogeneous equitable, we call them. However, maybe for some graph classes we can, and this is what we were hoping for. And that's how we started. We look at a small example, for example, and we realize, okay, this is an equitable partition and therefore needs to be weight equitable, is weight equitable. However, the path graph, a simple example, is already with this partition not equitable, but weight equitable. So we thought maybe we can kick out graphs without P4. That could be one first guess. And actually, we were pretty lucky because those graphs exist. So graphs without an induced P4 are called cographs. They're quite popular among the algorithmic community because they provide a graph class for which many algorithms are easy to solve. We will see why in a second. And actually, it's also known how to construct them. So there is this paper, I think this was maybe the first paper, where they give a recursive method how to construct them. So basically, well, Q1 is a cograph, the union of cographs is still a cograph, and the join of cographs is a cograph. And these are the operations that allow you to generate all cographs, actually. So they give a characterization. So what we could prove is like for cographs, if we focus on this graph class, all the two homogeneous weight equitable partitions are actually equitable. So whatever algorithm we find for equitable two homogeneous partitions is gonna hold also for the weighted by free, for free. So the next goal is now to just find such an algorithm. And in order to do so, what we did is like, okay, what is known about cographs? We really need to understand how they work and their structure very well in order to be able to find the algorithm to find these equitable partitions. So that took us a while, but then we realized cographs are represented in the literature by cotrees. Let me give you an example of what a cotree is. A cotree represents the union of vertices by 0 and the join of vertices by 1. So for example, in this case, we have this join by 1, so we hang the two vertices here. So the number of vertices of this cotree, the number of leaves of this cotree correspond to the number of vertices of this original cograph or tree. Yeah. And for example, if now I focus on these two, I join them by a 0 because it's just the union, the disjoint union. And then you keep doing the same for the remaining. So important thing to note, because we are going to prove our related result to this, is that the leaves of the cotree are just the vertices of the cographs. So the leaves of this cotree representing the cograph are just the vertices of these cographs. And actually, even more important, so we were pretty lucky, there exists a result that says that if this sequence representing the cotree, this sequence of zeros, ones representing the cotree alternates, then such a cotree is unique. So it uniquely represents the cograph. There is a one-to-one correspondence. And then what we prove as an intermediate tool for the algorithm is that if we have an automorphism P of a cograph, if we have such an automorphism of a cograph, that corresponds with an automorphism of the code tree, which acts as the automorphism does on the leaves, but then on the, so from the cograph to the code tree, and respects the 0-1 labeling. That was an important one. So this is kind of ideal for what we wanted to do. So this basically allows us to reduce the problem of finding these homogeneous equitable partitions to the problem of finding automorphism in a tree. And yeah, looking at the time, I will not spend too much time on the algorithm, but I just want you to give you the idea. So basically we have these two results. We know that this NP hard is very hard to compute two homogeneous equitable partitions because it's equivalent to compute involution without fixed points, and we know it's NP hard. And then we just prove that an automorphism of a tree with a fixed point for involution on the leaves happens if and only if you have an automorphism on the cograph. So let me skip this. This is the algorithm. Basically, the main idea is like you hang the code tree from a root vertex. We call it R, and then we look at all the subtrees falling from it. And then basically the criteria is to see how many subtrees are isomorphic. How many so there are various things to check here. How many subtrees hang and how many subtrees are isomorphic. And of course, checking isomorphism of subtrees is also a hard problem by itself, but luckily there was something called Edmonds algorithms, where basically it's an algorithm for detecting isomorphic subtrees in a actually good time. And actually this algorithm was even pushed to linear time. So we were pretty lucky because we managed to, at the end, put it all together, the idea to just record the tree from the root, look at subtrees. These two are isomorphic clearly, thanks to the Edmonds algorithm. If it's not isomorphic, for example, here you have W vertex hanging a little subtree, which has nothing to map. But then you go to the leaves. You go one level further, and then you apply it there. So this is a bit the idea. And then I will skip this part. It's just some experimental results. But for the sake of time, I prefer to focus on the open problems. So let me go to closing remarks. So the open problems, this is the first one. I have been talking, this problem was suggested by Willem Hammers. I have been thinking about it, but not too much yet. So this is still open. So the question is like, can we characterize a regular graph for which the Hoffman bound is tight? We have a tool now. We have a tool that says, if the partition, the color class partition is not weight equitable, then you can improve it by 1. Maybe that helps, I don't know, but maybe we need something else. And maybe let me say something like the computational output of such graphs. So I have been trying experiments here. It seems like most of them are bipartite, so they are trivially holding Hoffman bound, so we don't care about them. And not many of them are holding Hoffman bound and having chromatic number 3. So there is hope that such a characterization can be done. Can we say something about other eigenvalue bounds being tied for non-regular graphs, similar as it was done for Hoffman bound? Another open problem would be like, can we improve the Hoffman ratio bound for the chromatic number of some non-regular infinite families of graphs? So it could be like maybe exploiting the structure of the family. You can even go farther than, I mean, I improve it by 1, but maybe you can do more, just assuming some structural information of the graph family. Another thing that remained a bit intriguing to me is like, could we maybe investigate the polytope, which consists of these generalized double stochastic matrices, the ones that are not double stochastic because they don't add up to 1, but they are constant row sum and column. And finally, from the complexity point of view, of course, there are tons of open problems. So you can study the computational complexity of your favorite partition, equitable partition. So in general, not much is known. So it remains to be found algorithms for general graphs, NP hardening results for other types of partitions. So there is plenty of room here to work on. And then also find graph classes which admit partitions for cells that are not for these partitions that are not the trivial ones. So I would say like, we would like to know what happens, for example, can we characterize what happens for 3? When we partition the vertex set into 3 sets, can we say something about when is weight equitable or when is it equitable? That's also open. And well, I would like to finish just mentioning the two papers on which I base this talk. One is published, one is just submitted. And also I would like to mention, if possible, 1 year postdoc advertisement we have in Eindhoven is on the topic of algebraic combinatorics. So it fits perfectly this conference. So I thought just mention it here. Soon we will have the official opening online, but if you have questions or you're interested, you can already send an email. And I would like to finish with that. Thank you very much for your attention, and sorry for the technical issue.
Oh, Aida, thank you very much for your great talk and a lot of questions. Are there any questions to Aida?
Can I ask someone?
Yeah, sure, please. Yeah, Ilya.
Okay. You spoke about equitable partitions of cographs.
Yeah.
Yes. And do you know the papers of Gottfried Tinhofer?
No.
Spoke about compact graphs, which contains not only cographs, but also interval graphs and trees and many other graphs. And for them, for all of them, you can prove the same like in the tree case.
Okay.
So I mean that equitable partitions are somehow very closely related and maybe the same, I don't remember quite, with the orbits of subgroups. And also, he in fact proved, he gave an algorithm how to find them. Okay. It is exactly a one-dimensional Wissler-Lehmann algorithm. So in fact, you fix your favorite cells, apply the algorithm, and it contracts. It constructs the smallest equitable partition related to your original one.
Okay. So this is something I need to check. I was not aware of this paper. I know compact graphs have been studied in the context of equitable partitions by Gottfried. That's the original paper I also.
But after Gottfried, there are a lot of papers.
So I should, yeah, we should check that out because it could give new ideas. Thank you very much.
Thank you.
Any other questions to Aida? Well, actually, I'm interested which infinite families of non-regular graphs are you interested in? One of your questions. Would you please show the previous slides? Is it possible? Well, maybe next. Yeah. Do you have some families in your mind?
Not really, to be honest.
Not really.
No, I didn't have time to think too much on this. I mean, I have a feeling something could be done, but I don't have a good intuition which type of families one can look at. I mean, we have a condition already, but we need more than that. And I think some computational search would be beneficial first here to get an intuition of which families to look at. Yeah, I didn't do any preliminary result here yet.
So it means that you plan to start with some computational results.
Yeah, I think that would be a good idea, probably. At least to get a feeling, an intuition of where to look at theoretically.
I see. Yeah. Okay, thank you. Any other questions? Well, if not, then let us thank Aida again. Thank you.
Thank you very much.
Talk. Yeah. Thank you.